Today we are talking about measurements and data and Mario Kart. A measurement is simply an assessment of the value of something that we can make physically, and it will always have a number and a unit. There are 7 base units in the metric system that we can use to derive all the other units. Those are highlighted in blue on the right. We call these the SI units, which stands for the French Système International. They're essentially just the metric base units. From these, we tend to mostly use units like kilograms for mass, seconds, amperes, mole, and temperature in chemistry. We also use volume a lot, which you might notice doesn't have an SI base unit. Units like volume or force are actually based on other units. We call them derived units. Volume is distance cubed, or force is mass times acceleration, itself a derived unit. If volume is distance cubed, that means that we can actually multiply a length by itself 3 times, and it would be possible to convert a length unit to a common volume unit. If anyone is curious about Mario Kart, they should know that cc's refer to cubic centimeters, which are a unit of volume equivalent to 1 milliliter. Thus, the 150 cc tracks on Mario Kart allow for larger engines that have 150 cc capacity or 150 milliliter capacity, and those have greater max speed, which then makes the turns more difficult. Of course, they also have the removal of guardrails and more aggressive computer behavior, but the basic idea is that the cc's is a derived unit for cubic centimeters. The more you know. The SI units were typically based on something measurable. The kilogram was originally based on the mass of a liter of water, which is based on the cubic decimeter. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. Now SI base units have been redefined based on measurable quantities with very precise values. For the meter, it is based on the distance light travels within a given time. We typically use a system of metric prefixes in science, where each prefix functions as a multiplier for the unit. For example, a kiloliter has the same value as 10 to the third, or 1,000 liters. We use the same system for every type of unit, which means that we can cover a meaningful scope of units and measurements with just a handful of prefixes. The prefixes that are highlighted in the red box correspond to the metric prefixes that you are likely to encounter in life and in chemistry. And it's these that you should make sure you're familiar with. You should memorize them so they're accessible to you. Notice that the prefixes that are above kilo and below milli are all separated by powers of 3. So kilo is 10 to the third and mega is 10 to the 6th. And then past that, giga is 10 to the 9th. If you know the relative size of these prefixes, then you can figure out the actual value even if you've forgotten. So if you know that mega is bigger than kilo, you just go 10 to the third up from kilo, from 10 to the third to 10 to the 6th, and you can figure out that mega is 10 to the 6th. Because these prefixes are separated on the order of powers of 10, we actually only need a few of these prefixes to cover the measurements that we encounter. The customary system, on the other hand, is mostly a base 2 power system, at least in volume, and it takes a lot more units, most of which you probably aren't even familiar with, to cover a much smaller range of measurements. A teaspoon is about 5 milliliters, and a ton, the largest unit, is about a kiloliter. And don't even try to measure a yada liter in a customary system. To make matters worse, the customary system doesn't use prefixes, so different measurements have different relationships between units. There are 3 miles in a league, 80 chains in a mile, 11 fathoms in a chain, 2 yards in a fathom, 3 feet in a yard, 4 palms or 3 hands, depending on your persuasion, and a foot. As interesting as these units are, you can quickly see how onerous the customary system can be. Hence, we use the metric system. Of course, you could really pick pretty much any scale you want, as long as you have something to calibrate it by. When we're using the metric system, it's important that we're able to move back and forth between units with different prefixes. Setting up this type of conversion is essential to solving most of the problems in this course, and really gives you a strong basis for solving problems for the rest of this course, science, life, whatever noun you choose. This is a really important skill. To convert between units, we always need to multiply by a mixed unit fraction that has a value of 1. So you'd have a different unit on the top of the fraction than the bottom of the fraction. We call these conversion factors. Many of you have probably learned to convert between units in the metric system, and many of you have learned different ways to convert between units. I don't care what way you use. The only thing that I care about that all of you do the same is to get the units on the right part of the fraction. So if you're trying to get rid of a unit in the initial value, so in this case 2.5 microliters, it always has to go on the opposite side in the conversion factor. Since microliters is on the top in the initial value, 2.5 microliters, we put the unit on the bottom. Since we want milliliters to appear in the top in the product, we need to put that in the top, so the units of our conversion factor need to be milliliters per microliter. Some of you might have this part down already, others not. If you don't, this is the single most important thing for us to work through together to make sure that you succeed for the rest of this course. Don't wait. Reach out for help right now if you're struggling. We can work through this together lots of different ways until you get it. Once we have that down, there are a number of ways to make sure that we have the right values to go with all these units that we've already identified. Remembering that we're always going to have the same conversion factor equal a value of 1. So one way is to multiply each of the units in the conversion factor by the multiplicative inverse of the prefix value, so that the value of the top and bottom both equal 1. For example, the millif prefix indicated with a lowercase m has a value of 10 to the negative third. Since milli equals 10 to the negative third, multiplying 10 to the positive third will give the top section a value of 1 liter. Similarly, multiplying the micro, worth 10 to the negative 6, by 10 to the positive 6 will also give a value of 1 liter. So now the conversion factor has a value of 1 liter over 1 liter and will yield the correct value of 0.0025 milliliters. That's one way to do it. Another equally valid approach to setting up the conversion factor is to swap the value of the prefixes. So since micro, which is on the bottom, has a value of 10 to the negative 6, we put 10 to the negative 6 as a number on top. Similarly, since milli, which is on the top, has a value of 10 to the negative third, we put that 10 to the negative third on the bottom. Now the top and the bottom have values that are the product of both prefixes, but they are still the same as each other, and the entire conversion factor still equals 1. Again, this equally valid method still gives you the exact same values in milliliters. A third approach is to essentially count the steps between the two units. Some schools teach a process of writing down the units and counting the number of steps to move between units. In my experience, students who display their work in this way make frequent mistakes in the kilo to milli range where the units aren't spaced 3 apart. Another common problem students display is moving the wrong direction between units. You can formalize counting the steps using the actual number values for taking the power of the bottom unit minus the power of the top unit and putting that all on the top. If we apply that here, we end up with the top equaling 10 to the negative third, and we just put 1 on the bottom. Some of you intuitively do this already. It essentially relates units directly to each other. Others of you have memorized conversion factors between all the possible units that you could convert between. Since we're likely adding several prefixes to your knowledge base, take this opportunity to invest a little bit more time to understand why the conversion factor is set up the way it is, rather than memorizing more conversions. Again, if you can understand the logic of setting up a conversion factor and can apply it to problems, you've already set yourself up for success in this course. Most of our units are fairly easy to convert with the customary units that we might be more familiar with, pounds to kilograms, meters to feet, using the same logic of setting up units that we do in the metric system. We use a conversion factor where the bottom cancels out the top of the initial value, and the top of that conversion factor gives us a new unit. That works for things like mass, it works for distance, it works for volume, charge, and pretty much everything else, because everyone agrees on what a zero mass looks like. Everyone also agrees what a zero volume looks like. Temperature scales are some of the most difficult to convert because nobody seems to agree where 0 is. The same temperature, 0 degrees Celsius, is 273 in Kelvin, and it's 32 in Fahrenheit, and in Rankine it's 460. So you need 2 parts to most temperature conversions. A conversion factor to account for the degrees being worth more in Celsius and Kelvin than they are worth in Fahrenheit, and also a separate shift to account for the different 0 points. Most of you have seen some form of the Fahrenheit to Celsius conversion before. Notice that there's a fraction, here 5/9, and also a value that is subtracted. So the fraction corresponds with an adjustment of 9 degrees Fahrenheit for every degree Celsius or Kelvin, and the 0 temperature shift for between Fahrenheit and Celsius is negative 32 degrees Fahrenheit. Most of the problems that I have seen with temperature conversions come because people subtract or multiply in the wrong order. If you are diligent about units, it can actually solve that problem. You probably already know that water freezes at 32 degrees Fahrenheit, unless you aren't from the US. Since the offset from 0 is in degrees Fahrenheit, you always need to do that offset when the degrees are already in Fahrenheit. So if you start out with Fahrenheit, you need to subtract 32 first before you convert to Celsius by multiplying by 5 degrees Celsius per 9 degrees Fahrenheit. If you want to go from Celsius to Fahrenheit, you can't add 2 different units, so you need to multiply by 9 degrees Fahrenheit over 32 degrees Celsius first, and then only after you've converted to Fahrenheit degrees, then you can combine Fahrenheit with Fahrenheit. Both Fahrenheit and Celsius are used to talk about weather, depending on if you live in the US or pretty much anywhere else. In science, we use a mixture of Celsius, because the scale is conveniently referenced to water, and Kelvin, because 0 actually means something on molecular terms. To get from Celsius to Kelvin, all you have to do is add 273.15. It only has that 0 shift adjustment. Fahrenheit also has an absolute 0 scale. It's called Rankine. But scientists don't really use Fahrenheit, and regular people don't really care about an absolute 0. So there really are relatively few applications. Stinks to be a William John Macquam Rankine. Regardless of which system we use, all measurements are limited by the tools that we use to measure. For very few numbers can we actually know the exact value. That means that instruments that we use to measure something, for example, a ruler, a beaker, a graduated cylinder, they can all give us results that are more or less close to the exact actual value, depending on which instrument we use. Ideally, all of the instruments that we use are accurate, that is, centered around the true value. Accurate results are shown on the targets on the right, where inaccurate results are shown on the left. This is different and more centrally important than whether measurements are precise. Precision is how tightly grouped measurements are, regardless of whether they are accurate. 2 precise groupings of measurements are shown on the bottom. If I lift up my son and I say he's about 40 pounds, that's accurate, at least when I recorded this, but not really precise. That's okay though, because my description of about 40 pounds made clear that I was indicating weight accurately but with low precision. If I put him on a scale and it reads 42.5 pounds, that's still accurate but more precise. The more precise the measurement, the more useful it is. If I tell a doctor my son is about 40 pounds for medicine dosage, the doctor is still going to put him on a scale and get a more precise reading. But if I'm checking to see if he fits under the 100-pound weight limit on a chair, knowing that he's about 40 pounds is plenty. We rarely encounter exact values or exact numbers. One type of exact number that we can encounter is a literal count of every individual item, if you don't make any errors or estimations when you do it. I can get up to about 5 as an exact number, and then my counted numbers get inexact. The other exact number is a definition, like I know there are exactly 100 centimeters in a meter because that is by definition true. Note that this is not true for conversions between the US and metric system. They're not defined against each other, and so those values are not exact, they're measured, and they're only accurate to as many decimals as you can know them. Again, every measurement other than literal counting is inexact, and we know only as much as our tool can tell us. The ruler is displayed to read the same object that's shown, that rod. Give an example. The ruler A on the left only gives markings at centimeter marks. We know for sure that the ones unit is 3 because we can clearly see that the object is between 3 and 4. When an object gets measured between two lines, we estimate the position between the lines to give the final digit of our measurement. This digit is then considered estimated, and it is reasonable to get a different value for every time you measure it, or every person who measures it. It is shown as 3.7 on this figure, but I could have just as easily called it 3.8 and been correct. The ruler on the right has more markings, and so now we can see the object is between 3.7 and 3.8. So the ones and tenths unit, 3.7 are both certain, and we can estimate 3.74 or 3.75. Notice that 3.7 conveys information about how precise the measurement, as does 3.74. Recording the number 3.74 tells everyone that you used a more accurate instrument. For this reason, it's really important to record all the units possible for any instrument, but never any extra. XKCD, a gloriously nerdy webcomic, gives another way to understand the meaning of recording different numbers of significant figures using degrees, latitude, and longitude. Depending on the number of decimals included in the measurement, they mean very, very different things, and sometimes implausible things. We run into issues with specifying how precise a measurement actually is in some cases, because zeros are used both as a meaningful part of a measurement, but also as placeholders. We can start from an understanding that any number that isn't zero is always going to be a meaningful part of a measurement. Otherwise, we wouldn't include it. We call this significant. Anytime a zero is between significant figures, those zeros are also significant. You can't have a hundreds unit and a ones unit be significant without the tens unit also having meaning. So 101 Dalmatians, 101, the 0 is going to have meaning because both ones have meaning. And finally, anything that's after significant figures and a decimal is also significant. Otherwise, there'd be no point in including it. So in the number shown, the 3 zeros on the left are not significant because they're just making sure the other digits show up in the right place. But everything to the right of the 7 is significant. Using a lot of zeros as placeholders can make numbers difficult to read and makes significant figures a little less obvious. Sometimes we'll use scientific notation to describe this. Scientific notation, most simply put, is writing numbers in such a way that the only digits displayed are the ones that are significant, no more, no less. The way scientific notation is taught in some curricula would have you believe that it is the only way that scientists ever display numbers, which is certainly not the case. In practice, scientists will use metric prefixes to minimize placeholders, and will only use scientific notation in rare instances. However, scientific notation is useful pedagogically because it gets us to think about which digits are significant, and the ways of thinking for scientific notation are similar to the ways that we think about metric conversions. This first example displayed already displays only the significant figures, 1, 0, 1. We can absolutely put this into scientific notation as shown. 1.01 times 10 to the second is the correct scientific notation for 101 Dalmatians, but it isn't actually any more useful than the original number. Similarly, displaying 0.250 milliliters of blood in scientific notation can reduce the number of placeholding zeros, but it actually makes the written number longer. Most scientists would either keep the 0.250 milliliters or instead report as 250 microliters. 299,800,000 is the speed of light in common units to 4 significant figures. But here, it would be unclear if the 0 after the 8 is still significant, and changing to megameters per second, while an awesome unit, actually makes a lot of calculations that we do difficult. The speed of light and other physical constants are the most common application of significant figures, particularly physical constants that are very large, like the speed of light, or very small, like Planck's constant, which is used in waves calculations. It should be fairly easy to take things out of scientific notation. All you have to do is complete the calculation that's described. When you put the numbers into scientific notation, it's really just moving the decimal so that you only have one non-zero digit before the decimal place. If the decimal is moving left, like in the Dalmatians example, the power of 10 goes up for every position you move to the left. If the decimal is moving to the right, like in the blood example, the power of 10 goes down for every position. Again, you can make sure that you went the right direction by just completing the calculation. These are really easy to check your work. If you calculate out your scientific notation and you end up with a different number, you are probably assigning the wrong sign to your power of 10. Again, if the scientific notation is displayed correctly, the only digits that will be displayed are the significant digits, which makes understanding the precision of a measurement really straightforward. And if a number is in scientific notation, the last digit reported will always be the estimated digit, the one that varies between individual measurements. Suppose I look at a group of people, and I estimate that there are about 20 people. They're a strange group, and I'm not really sure what's brought them together other than an unexplainable urge to congregate in large groups. I didn't count, so the 2 of the 20 is an estimated digit. I really don't know the number to any more precision than that. Now suppose one person left. His name is Gregor Samson, and he never really formed any real connections to the group anyway. Hey, look, right where Gregor was. It was pizza. Pizza brought everyone together like a glorious beacon of peace. Anyway, I wouldn't suddenly know that there are exactly 19 people because I didn't know that there are exactly 20 before. I'd still say there are about 20 people. That's because you can't know the value of a calculated number to any more precision than the least precise number you have available. Turns out, it works the same way in all calculations involving significant figures. Whenever you are adding or subtracting numbers, the least precise number controls how precise the result is based on the decimal place of least precision. So one number here is only precise to the 10th digit, so the actual result can only be accurate to the 10th digit as well. For multiplication and division, you are also limited by the least precise number, but now based on the total number of significant figures. Since the 2.57 only has 3 significant figures, the resulting product should also only be reported to 3 significant figures. Of course, if you're paying attention to significant figures, you're often rounding to get the right number of significant figures. Never just stop at the last significant figure. Always round based on the remaining decimals that you won't keep. So as a general rule, 5 or higher is going to make the next digit go up, and the rest will go down. There are more robust rules for rounding well and other calculations that we'll talk about in analytical chemistry. As a quick teaser, this is what you have to look forward to. Often experiments are combinations of many measurements. While we could try to propagate the right number of significant figures through all of our calculations, this is a little bit difficult. We sometimes do. However, we often instead try to relate multiple measurements by using statistical measures of precision instead. While we still record individual values with appropriate precision, we deal with experimental values as aggregates, like means and standard deviations, to indicate precision. To indicate precision, we will then calculate a standard deviation using the equation shown on top for a set of experimental measurements. So we have to take a number of measurements. Doing this calculation is easiest to do in Excel, which handles doing the same calculation over and over again fairly easy. And there are functions that automate many of the calculations. So we're going to use these to show us a little bit about how to make Excel work. Every good Excel file has values clearly labeled, so we'll start there. Hopefully you can clearly see that we've been testing how much wood a woodchuck could chuck, and by the fact that we have data, that a woodchuck would chuck wood. Standard deviation for samples is calculated by first calculating the average values, x with a line over the top, which we call x bar. You have to do the calculation of the average value before you can do any of the rest of the calculation. If we didn't already know how to do this, we could click the FX button, which you can see highlighted in red now, which would bring up a pop-up window that we can use to search for a specific function. Then we can type in average, and it would give us a list of the closest matches. We can calculate average by typing equals average, then a parentheses, then a cell locator, which is a letter and then a number, and that cell locator would be the first value in our average. So in this case, our average starts in cell B3. Then after that, we put a colon and the cell locator for the last value in the average. So if we go straight down the line, the very last one is in cell B7. Then you can also generate that same range by highlighting, clicking and dragging over the cells that you want. Close the parentheses and type enter, and it will actually calculate the result automatically. So here it shows that we have 3.48 as our average value. Each individual measurement needs a difference calculated as well. And then we need to square the difference also. We can easily do both of those. Note that in the function for the difference, the cell reference for the mean, B8, has a $sign in front of the B and a $sign in front of the 8. That's called an absolute reference, and it allows you to click in the bottom right of the cell and drag down to autofill all of the formulas below. You can see what the cell will look like if you're in that corner shown on the screen under C3. Any references to cells will be changed relative to the original cell unless they have a $sign in front. So when I clicked and dragged to autofill the first formula, equals B3 minus $B$8, the next line becomes equals B4 because it's one line below the original B3. But $B$8 doesn't change because of the dollar signs. You can also just put a $sign in front of one part. If you want to change the column but not the row or vice versa, you could do $B and just 8, or you could do B$8. Anyway, we have all of the squares now, and we can use a formula for sum to add them all up. There it is. I know that you can count the number of samples and subtract 1 to get the n-1 that we need on the bottom, but if we had more time to experiment with woodchucks, we might not want to count every single data point. We can use the count function to do that and subtract 1. Divide the sum of squares by n-1 and take the square root of the result, which is also a function, and we have the standard deviation. That gave us some good practice seeing some of the Excel functionality and hopefully helped us to understand how standard deviation is calculated. We most often do this with lab data, and it turns out that Excel is usually available for lab data and is good at doing functions. It's even easier in Excel to use the equals standard deviation stdev.s function, which gives us the exact same standard deviation of a sample. Hey, we did it right. So we've been able to establish both the experimental average, 3.5, and the standard deviation, 1.6. We generally report it as an average plus or minus the standard deviation at this level, although we get a little bit more nuanced later. The standard deviation is one of the ways that we can talk about precision. If we want to talk about accuracy instead, we use a percent error, which is defined as error in measurement over accepted value, multiplied by 100 to express as a percent. Error in measurement is the experimental value minus the actual value, and can be positive or negative, which means that the percent error can also be positive or negative. When we actually want to calculate the percent error, we need some sort of actual value, usually from the literature. Turns out, someone else has figured out how much wood a woodchuck could chuck based on the actual amount of dirt they actually chuck each day. Because we care about academic honesty, let's include a citation. Unfortunately, the units don't actually match up with our experiment. Our experiment has units in sticks per minute. This reference has values in 700 pounds of wood per day. So we need to use conversion factors to convert these. We can use a measured definition of sticks per pound and the exact definition of minutes per day to convert to an actual value of 3.6 sticks per minute, as shown. We calculate the percent error on the very bottom, as is shown in this formula. We take B8, the average, and subtract the actual accepted value from B16, and divide that whole calculation by B16. Notice that I didn't multiply by 100% in the Excel file. It's because percent is just a different way of writing a decimal number. Instead, I click the percent sign way up at the top of the home screen to display the number as a percent automatically. Not that you couldn't do it by multiplying by 100% too. This is just a nice, clean way of displaying the unit data. I've integrated most of our discussion of how to use the formula bar and display data in Excel into our discussion of standard deviation and experimental error. We also often will display graphs using the data we have in Excel, which is convenient because I've noticed an interesting thing about our woodchuck chucking data. We have a pretty wide range of chucking capacity, so wide in fact that I probably should have displayed the average and standard deviation as only one significant figure, as 4 plus or minus 2. Which makes me wonder if there's another factor that's affecting the chucking capacity, a confounding variable, if you will. So I went back to my absolutely real notebook, and I realized that in the interest of getting representative data, we had used a different woodchuck for each run, and in the interest of completeness, had recorded a complete health profile of each woodchuck. I imagine that the amount of woodchuck present may actually account for some of the variation I would see. So now I'm going to enter a new label for the run numbers, recorded of course in SI units of kilogram, along with all the data I had so meticulously recorded in an earlier, definitely real experiment. There are a few problems with the way the data is displayed. One is that while I typed in 2.0 for A4, Excel just keeps on displaying 2 over and over and over again. Excel doesn't know about our significant figure rules, it just treats everything as an exact number. I can get it to display correctly though by looking for the number section on the Home tab and pressing the button to move the decimal place over, that's that one, to make the 2.0 display correctly. That's better. I also want to see if there's a relationship between mass and wood that a woodchuck could chuck, so I want to sort the data. Turns out there's an entire menu selection for data, and if I click on it, there's a section for sorting and filtering. I don't want to remove any data, that doesn't sound ethical, so I'm just going to click this button that sorts in an ascending order. It seems a little bit more clear that there might be a relationship now, but I want to be more sure. This is where art and science meet in the gloriousness of our liberal arts education, because nothing displays data better than a visualization. I can create a chart through the Insert Main menu option. There are of course lots of options, but the form of a chart can display really specific things about data, so we need to be careful about which one we choose. Because we only know the values at discrete points, we tend to use scatter plots in science. That's this button, which brings up this window, which allows me to select the points only option. You can manually arrange and enter data, but for simple graphs, you can have the x-axis, the independent variable, listed in a column on the left, and the y-axis, the dependent variable, listed on the right. And by simply highlighting the entire region, that will allow Excel to interpret this automatically, which gives a graph like this. We looked for a relationship, and we have observed it. An important note though, we haven't proved massive woodchucks could chuck more wood. We've observed it in a small sample size and can further design tests for this relationship. As drawn, it doesn't have any axis labels, which is actually kind of a big problem because the graph doesn't mean anything if you can't tell what's being graphed. When the graph is selected, the Chart Design tool main menu pops up and is at first automatically selected. You can choose from the quick layouts to see which layouts are available that have axis titles. It doesn't matter which one you choose as long as it has axis titles that you can edit. I chose and edited the top left to show a graph like this. I left the other graph partially displayed so you can contrast the two graphs. They both display the same data, but by labeling the axes and giving a title, a reader can actually interpret the data. The last thing for today that we have to learn about graphing is to add a trend line, also known as the line of best fit. If you click on any data point, it highlights the whole set. Right-click or Apple-click with the data selected, and you can click Add Trend Line. A trend line will be drawn through the selected data, and the Format Trend Line option will appear. If you scroll to the bottom, you can find Display Equation on Chart and Display R-squared value on Chart, which are both typically checked for a display of scientific data. And now we have it, an observed relationship between woodchuck mass and chucking capacity. the wonders of science.